SwayamPrabha. Digital India. Educated India.
Hello, welcome to today's Biomathematics lecture. We have been discussing differential equations. So, in the previous lecture we discussed the first part of differential equations, very simple ordinary differential equations. Today we will have the second part on differential equations. So, the title of this lecture is Differential Equations Part 2. We will go ahead from where we stopped last time in the last lecture. So, where we discussed simple differential equations of the form. So, let me write here the simple differential equations we wrote, like something like dy by dt is some function f either of y or a t, something of this form. So, such differential equations, as we said, is called ordinary differential equations, and today we will go and see. So, we already discussed a few examples in a few different cases, which is including bacterial growth, and today we will go and see which other context in biology, where in biology you would need to think of differential equations. As you all know, one of the important things in biology as well as in physics in general, or in general in nature, is a relation between energy and force. So, you might have heard of potential energy, like electrostatic potential energy, where charges attract with each other. So, the force with which they attract and the energy, they are related with each other. So, they are related through a very simple differential equation in some sense. So, today we will discuss, first we will discuss the relation between the force and energy. So, let us look at the relation. The relation between force F and the energy E. So, this energy here could be potential energy. So, some places you might see this V. So, here I am using the notation E for energy. Typically you might see it some other, in some books you might see it as V, or many other U, in some other places you might see it as U, but essentially what we are representing is the energy, the interaction energy. We will, as we come to different examples, we will see what E is. So, the relation between F and E, that is, if you know the E, the way to calculate F is to calculate minus dE by dr is F. That means the first derivative of energy, dE by dr with a negative sign, will give you the force. So, if this is like a differential equation, this is like a differential equation, dE by dr is equal to minus F. So, one can integrate this equation and get energy, because if you know the force, you can calculate energy by this by solving this simple ordinary differential equation. So, let us think of some simple energies. So, in biology, like there is all energy associated with proteins, their configuration, so on and so forth, but here we will take a very simple case. So, it turns out that one simple way of thinking about proteins is think about spring. So, spring is something like can extend and compress and all that. Proteins can also be pulled out, so it can be extended in some sense. They get folded, so they come to a compact state from where you can pull out the proteins. So, essentially the simplest way of thinking about protein is to think about springs and charges. Those are the two simple interactions that one can think of easily, and they correspond in some sense with proteins. So, we will, in this course, to understand the concept, we will think about the simplest example, that is a spring. So, let us take the case of a spring and have a look at this slide. The spring has force that is proportional to the distance. Now, what is force and what is distance? So, what is the distance here? So, let's try and understand a bit. So, have a look at this drawing here. So, you have drawing here this distance. So now you have a spring which you have some certain distance here which we call r. So it turns out that the more the distance, the more the force is. So you can always see, all of you have taken a spring or go and take a spring and try pulling it, try applying a force. The more you pull it, the more force you have to apply. To hold it a far distance, to hold it a distance r, you have to apply less force. To hold the two ends of the springs farther, you have to apply a larger force. So it turns out that the force and the distance are proportional to each other. So that is why the force is proportional to r, the distance. But it turns out that when you hold it, you are experiencing a force in the opposite direction. So to show this direction, we have a minus sign. The spring force is proportional to minus r. So this is the basis of what is written here in the slide. F is directly proportional to minus r. So the more the force, the more the distance between two ends of the spring, if it is r, the more the distance, the more force you have to apply, but the direction is in the opposite. So there is a minus sign. So we know that F is, you can remove this proportionality by, you can equate this with a constant k, where k is, you can think of k as a spring constant, which depends on the property of the spring. If the spring is made of some particular material, you will have particular k. If the spring is made of some other material, you will have some other k. So k essentially depends on the material property of the spring. So we know that F is minus kr. Now let us go back to the old relation which we saw previously and think about this. So we saw this relation that dE by dr is minus F. That is what we said. This is the relation between energy and force. Now if we substitute F is equal to minus kr here, what you would get is dE by dr is equal to kr, or dE is equal to kr dr. That is, I can take this dr on this side, I can multiply both sides with gr in this part of the equation, and I get d is equal to kr dr. Now you integrate both sides, integral dE is integral kr dr. So what you get is E is equal to kr square by 2 plus constant. So this is what the integral of dE is E, integral of kr is k is k and r is a constant, integral of r is r square by 2. So basically what you would get is half kr square plus constant. So half kr square plus constant. So what you get is energy is half k r square plus a constant. We always saw that this constant is a part of the constant of integration. Whenever you do an indefinite integral, you have to have a constant which now depends, which can be fixed by boundary conditions if you wish. If you know the boundary conditions of the energy needed to full from here to here, if you know the, if you say that, then you can fix this constant. But otherwise, a constant, you can always add a constant to an energy. It turns out that what matters is the derivative of energy, because in experiments what you can measure is always force. It is difficult to measure energy. So whatever be this constant, whatever be the value of this constant that we are dealing with, the derivative of this dE, when you calculate the dE by dr, the constant will go to 0. So you can put any constant you want in principle and still you will get the same force. So now let us quickly plot this and see, let us get a feeling for this plot. So let us have a plot here. Let us plot energy versus r. So you will get a parabola kr square. I am not plotting this left hand side because in this case r is only positive for a spring. So this is what half k r square. Now even if you add a constant to this, the shape of this curve will not change. So, let us have a look at this plot once more. Even if you add a constant to this, the curve will become something like this. So, essentially it will get shifted, but the shape of the curve will not change. So, this is half k r square, and this is a half k r square plus a constant. So, let me plot this little more carefully here. So, let me plot this little more carefully in the next one. So, let us plot here. So, this is half k r square, which is energy versus r. Now, we can add a constant to this, and if you plot that, you will get something like this. It is exactly the similar curve parallel to this. I haven't drawn it very properly, but it is just like adding a constant everywhere. The shape of the curve will not change. So, essentially what you want to learn is that the force, which is derivative of this curve at every point, if you calculate the derivative at any point, if you calculate the derivative here, you should get the same derivative, because you are essentially adding a constant. So, basically that the force will not change. Now, you can also do this by saying that you can pull the spring from this place to this place, and you can ask the question, how much is the energy cost to pull the spring from here to here. So, let us do that here. So, have a look at the slide here. So, if you look at the slide, what you have, this equation is integral dE is integral kr dr. So, now let us write that here. So, let us write integral dE is integral kr dr. Now, first you had this particular r, which is, let me call this r1. Now, I am pulling the spring to a greater distance, which is r2. So, I am pulling from r1 to r2. So, I have this spring which is r1, then I am pulling to a length r2. You can ask the question, how much energy it costs to pull from r1 to r2. So, then this integral goes from r1 to r2. So, this is energy, and here r1 plus r2. So, k r square by 2. Now, in the limits r1 to r2. So, if you have, this is the integration with the limits r1 and r2. So, this is done by, you can write integral of kr dr is kr square by 2, and you have to apply this limits. So, the way of applying limits, as you learned, is that k into, so this 2 is also a constant. So, I can take this 2 out. So, basically r2 square minus r1 square. So, this is the energy. So, this is the energy needed to pull a spring from r1 to r2. If this is r1, this is r2, the energy needed to pull a spring from r1 to r2 is k by 2 into r2 square minus r1 square. So, this is the answer. So, this can be written as k by 2 into k by 2, you can say k by 2 r2 square minus k by 2 r1 square. So, you can also write like this, k by 2 r2 square minus k by 2 r1 square. So, this is exactly same as that. So, this is basically the energy needed to pull a spring from r1 to r2. So, this is essentially the energy difference. If you look at this equation once more, a little more carefully. So, let us write it here separately. So, let us write that what we got is energy is k by 2 r2 square minus k by 2 r1 square. So, this is nothing but energy to keep this. So, this is one energy which is E, let me call this E2 and this we call this E1, where E2 and E1, so this is R1 and this is R2. So, this is the energy of this spring is E1 and this energy of this spring is E2. So, then the energy difference is basically E2 minus E1. So, basically what you find is that the change in energy, the energy needed to pull from here to here is the energy difference between these two, and this thing you can get by integrating this particular equation, this particular differential equation. So, this is the simplest case that we learned. Now, let us go to the next case, for example. So, let us, which is basically charges. So, as we said, if we learn about springs and charges, we learn a lot about biological system. So, let us take the simplest case of a charge system, which is two positive charges at a distance r apart. So, these are two charges plus q and minus q, and the distance between them is r. And we know that in such a case, what is force? The force is given by Coulomb's law, and it is F is q square divided by 4 pi epsilon 0 epsilon r square, where epsilon 0 and epsilon r you know as the permittivity of at vacuum and relative permittivity. So, you know these constants from your school classes. So, our capital R here is the distance between these two charges, and this is the force, and this is the famous Coulomb's law. Now, knowing this, how do we calculate energy of the system, energy of this charge systems? So, the energy of this charge system can be calculated the same way by integrating the equation as you see here. So, the equation here is dE by dr is minus F. So, dE by dr is minus F, and the F we know. So, let us find out what happens if you substitute this F here. You get q square by 4 pi epsilon 0 epsilon r square. That is what you substitute for F. This is what you get. So, essentially you can take this dr this way, this side, or multiply both sides by dr, and you get dE is q square by 4 pi epsilon 0 epsilon r square dr. So, this is basically rewriting this equation, and now we can integrate both sides. So, q is a constant, 4 is a constant, pi epsilon 0 epsilon r, all of them are constants. So, you can take out all of this, and you can have just integral of 1 over r square dr. So, what is integral of 1 over r square here? We know that integral of r power x power minus n, or 1 over x power n, is if you have integral of x power minus n, it is x power minus n plus 1 divided by minus n plus 1. We know this. So, let us have a look at it. So, if you do this, integral of r power minus 2 dr, that is what you have to calculate, and we know that integral r power minus 2 dr is r power minus 2 plus 1 divided by minus 2 plus 1 plus a constant, and this is r power minus 1 with a minus sign. This is what integral r power minus 2 dr. So, essentially you will get r power minus 1 is 1 over r with a minus sign plus a constant. So, have a look at this here in the slide. You get a minus sign extra, this minus sign goes away, and q square 4 pi epsilon 0 epsilon r remains the same, and r power minus 2 becomes 1 over r plus a constant. So, this is basically, you know that this is nothing but the potential energy of two charges. So, the potential energy, when you have two charges, the potential energy of the system is q square by 4 pi epsilon 0 epsilon r by r. So, this is the potential energy. Do not confuse this E, this is here, E is not electric field, this is potential energy. I just use the symbol E for energy. So, some places you in the textbooks you might see this as V. Typically, this is what is used, V. So, you will see that this is typically written as V. So, some places you will see that potential energy. So, let me write potential energy of two charged systems is q square by 4 pi epsilon 0 epsilon r square plus a constant, and that constant can be anything. That does not change the force. Whatever be the constant, again the force remains the same, because the derivative of energy is force and derivative of any constant is 0. So, again you have the force. Again here also you can do this integral is the limit. You can do what we had here is, if you look at the slide, what you have here is integral minus q square by 4 pi epsilon 0 epsilon r integral 1 over r dr. You can do this from r1 to r2 again. This is the same question. What are we asking here? We are asking, if you have charge as this distance, and if you move this charge from this distance to this distance, how much energy it costs to move this charge. So, again you can do this. So, if you do this integral, so let us have a look at what you end up here. Basically what you have to do is q square by 4 pi epsilon 0 epsilon r is a constant, r1 to r2 1 over r square dr. That is what you have to do. So, in the previous one you had integral 1 over r square. So, this is the energy we have. So, integral of this in the limits r1 to r2 is nothing but, so this is equal to, if you do this, this constants, this constant will exactly remain the same, q square by 4 pi epsilon 0 epsilon r, and integral 1 over r square, as we saw, is 1 over r with a minus sign. So, we had a minus sign here. So, that minus sign goes with a plus, it becomes plus here in the limits r1 to r2. So, you have to apply a limit to this 1 over r. So, essentially what you would get is q square by 4 pi epsilon 0 epsilon r into 1 over r2 minus 1 over r1. This is what essentially the potential energy difference, the energy difference between 2 points, or in other words the energy needed to bring this charge from r1 to r2. If you want to move this charge, let us say these proteins keep moving, when they change their configuration, the charges has to move from one place to another place. So, that much energy has to be put in to move one charge from one place r1 to another place r2. So, this is basically what we have seen here, is the energy needed for a charge to move from r1 to r2. Again we got this by solving this simple differential equation. So, this is all a part of calculus where you can apply all these ideas, simple ideas of integration or differentiation, to understand about forces, bacterial growth, energies and motion. So, when we talk about motion, the next question is, how does this differential equation governs motion? So, that is what something we will come and see later in this talk, but there is another simple differential equation which we have to understand. So, another thing that is often comes in biology is concentration. So, concentration varies within the cell, or concentration can vary within a particular region. So, when this concentration varies, diffusion can happen, that you know. So, our aim is to try and understand this diffusion from this perspective of differential equations. So, there is something called diffusion equation, but at this moment immediately we will not go directly to the diffusion equation, which is a bit complicated for beginners. So, first we will try and understand how the concentration gradient or the difference in concentration, how do we represent that through a differential equation. So, let us have a look at this slide. So, let us imagine such a cell having uniform concentration of something. So, this is a green thing here, which is, let us say, some protein. It is almost uniform all over. So, if we want to make this statement mathematically that this is uniform all over, the way to make the statement is exact following, that is what written here. We can say that dC by dx is 0, that is, the c does not change with x. So, here the x is this distance. So, let me draw here. So, we had, have a look at this drawing here. So, we had, let me call this x as this distance for convenience here. So, this starting from here, the x goes in this particular way. So, all over here the concentration is pretty much the same, let us say uniform concentration everywhere. In that case, what you want to say is that the concentration does not change with x. So, if you say c as a function of x does not change, that means dC by dx, the change in c when you change x is 0. That means the concentration does not change. This only means that c is a constant. How do you know that? Because you can integrate this equation. I can multiply both sides with dx. So, you will get dC equals 0, because you multiply 0 with anything is 0. Now, you can integrate this, and you can integrate this. So, 0 is anyway a constant, as there is a constant of integration. So, you will get c is equal to a constant. So, that is how you integrate by this equation. So, essentially what we did here is that we conveyed a message that the concentration is uniform across the cell or this particular region that we saw, and this is mathematically expressed the way that dC by dx is 0. Now, let us look the next case where it is not uniform, but is slowly varying. How do we express that? So, have a look at the next one. So, from here to here the concentration is slowly increasing. Here the concentration is less, here the concentration is more. So, the concentration is slowly increasing. So, how do we say that the concentration is slowly increasing? So, the way to say this is that dC by dx is a constant. So, that means the change in concentration when you change x is a constant. This is the simplest thing, constant change in concentration, and you can integrate this equation as we always do, multiply both sides with dx. So, dC can be written as k dx, and you can integrate both sides like we do. So, c is a constant, integral of dC is c, k is a constant, integral of dx is just x. So, it's kx plus a constant. So, that means it's a uniform, it's a concentration gradient, there is a concentration gradient. So, in this point, so this thing is called a concentration gradient, the dC by dx, the derivative of concentration. But when you talk about the real gradients, there is something more we have to understand. We have to incorporate the idea of the vector, the direction. So, whenever we talk about the force and whenever we talk about gradients, we have to include the direction in this. There is a gradient in a particular direction. As we go from here to here, there is a gradient. We have to bring this idea of gradient here. We will discuss that. How do we bring about this idea of direction here? We have to incorporate some ideas from vectors. So, the vectors that we discuss, we will see how do we incorporate the idea from vectors to say here, to incorporate the direction in this gradient. Essentially, we want to say that the concentration is increasing in this particular direction. In which direction is concentration changing? So, we have to incorporate this idea of vectors here to exactly mathematically convey this idea. So, we will discuss how do we do that in another lecture, but at this moment we basically just want to understand this differential equation dc by dx is a constant, and the integral of that is c is equal to kx plus constant. That is what the integral is. So, we know this much. Now, we will go to a different thing. So, we said concentration is one of the important thing in biology. Another important thing is again the force, but there is force associated with motion. So, we saw force and energy. Now, what we will see is that force and motion, because things move around, molecules move around, and when molecules move around in biology, you have to have some force. And how does this force and the motion are related? Because basically, for example, you know that protein which is completely straight, they fold up into a folded configuration. So, the protein which is unfolded, which is not in this fold, which is in some random configuration, they all come together and fold. So, there is some force making this protein fold. In other words, the protein molecules are moving in a particular direction, so that they end up in a folded configuration. So, how does this force and motion, how are they related? And they are related through a differential equation, and this is what we will see today. So, let us have a look at this. So, before discussing this, we should understand one thing about differential equations. So, there is something called second order differential equation. So, what we have discussed so far is called the first order differential equation. So, let me just say what I mean by first order differential equation once more. So, we said things of the form dx by dt is something. So, here there is, we only use the first derivative. So, such things are called first order ordinary differential equations. We will see what are we will see some other kind of differential equations. So, but whatever we saw so far are first order ordinary differential equations. Now, we will go and look at something called second order differential equations. So, have a look at this slide. If you have d square x by dt square is something, so there is a this is a second derivative. So, such things are called ordinary differential equations. So, now we will immediately come and see what are this example, what is the example of this, because when we say about force and motion, we have to deal with second order differential equation, which is one level up from what we discussed so far. So, now how do we learn about force and motion? So, we all know that something that connects the force and motion is this famous equation called Newton's equations, where Isaac Newton proposed these equations in way back in late 60s, like in 17th century and early 18th century. So, in late 1600s and 1700s, Newton discussed about these equations. So, the equation that connects the force and motion are called Newton's equations. So, let us see an example. So, we can think of an example which is d square x by dt square is some constant f by m. So, this f is a force. So, Newton's equation is essentially, as you all know, is that d square x by dt square is the m. So, this is called Newton's equation. So, you all know that f is equal to ma. This is the Newton's equation that, as all of you know. Now, a acceleration can be written as dv by dt, that is a is acceleration and acceleration is change in velocity by change in time, dv by dt, and v can be written as dx by dt, that is change in position divided by change in time. So, if we dx by dt is v and d by dt of this is acceleration. So, this whole thing can be written as d square x by dt square. So, this is essentially d square x by dt square, this whole thing is written as d square x by dt square. So, essentially acceleration can be written as d square x by dt square and acceleration is force by mass. So, this is basically Newton's equation, and the simplest Newton's equation you can think of is something falling under gravity. So, let us say this pen is, if I leave the pen, it will fall under gravity. So, the falling of this pen or any object that is falling under gravity can be described by this equation. If you say F is equal to mg, if I say F is equal to mg, I get this equation which is d square x by dt square equal to g, which is a simple equation which is basically equation of Newton's equation for an object falling under gravity, where g is acceleration due to gravity, which is a constant which is 9.8 meter square per second. So, g is a universal constant for in our earth, which is 9.8 meter per second square, and once we know this g, we can solve this differential equation d square x by dt square, the second order differential equation, and get a solution for x, where x is the position of the object falling. So, let us try and understand a little more what does this equation actually mean. So, let us try and understand a little more. Let us say an object, let us have a look at here. Let us say an object is falling from here, and so this is the object which is falling. It started falling from this particular position. So, let x is the distance from the initial position at any point. So, I consider x as the distance from, so x can be thought of as a distance from any point. We will come and discuss what is x basically. X is basically the distance of this object falling. You can measure either the distance from the ground up or from some fixed point. So, we can decide where you want to take this distance, but x is essentially this distance. And how does this distance vary as a function of time? So, that is what this equations describe. How does this distance, for example, distance from the ground, how does it vary as a function of time, or distance from a fixed point, how does this distance vary as a function of time when this object is falling? So, that is this equation describes. So, again let us have a look at this equation, d square x by dt square. How does this x, which is the distance from the earth for this particular object that is falling, is changing with respect to time? That is what the question we are asking. So, it turns out that this can be integrated the way we did for all of the cases. So, let us have a look at this next slide. So, this slide says d square x by dt square can be written as d by dt of dx by dt, as we saw. Once we write this in a particular way, this is basically equal to g, this is our equation. Now, dx by dt, as we said, is change in position by change in time, is nothing but velocity v. So, v is dx by dt, and this is dv by dt is equal to g. So, the equation becomes dv by dt equal to g, and as this is a simple ordinary differential equation that we have been seeing all in this class, in the previous class, and such an equation as an immediately we can see that such an equation has a solution which is V is equal to gt plus a constant, and that constant, as we said previously, is basically the velocity at time equal to 0. So, essentially you can write V of t is equal to gt plus V of 0. If you have confusion, let me do this little more carefully. How did we do this? So, dV by dt was g. This was our equation. Now, we can integrate this by dV is g dt and integrate both sides. So, basically V is equal to V as a function of time is equal to g t plus a constant. Now, how do we calculate this constant? Put time equal to 0. At time is equal to 0, what you have? V of 0 is equal to V at time equal to 0 is this constant. So, essentially what we have, you substitute this thing back in the above equation. So, then you get V of t is equal to g t plus V of 0. So, this is essentially what I have written here. This is exactly what I have written here. V of t is g t plus V of 0. So, you know, as this is falling, the velocity seems to be increasing. So, if you plot this g is a constant, this is like y is equal to mx plus c. This is a straight line. So, that means as an object is falling, its speed is increasing, its velocity is increasing. So, that is what it says. That is what the first part of the solution tells you, that as an object is falling under gravity, its speed is increasing. That is what the first part of this equation says. V t is equal to g t plus V 0. Now, this is only the first integration we did, and we got just the velocity, and to do the one integration we needed to understand one constant of integration V of 0. Now, let us do the second integration. The second integration is, so we have, as of now we have V of t is g t plus V 0. Now, we know that V is nothing but dx by dt. If we substitute V of t is dx by dt here, we have another differential equation now. Now, we can integrate this differential equation by, as we typically, this is again is a first order differential equation. You can multiply both sides with dt. So, what you will end up is integral dx is integral gt plus V 0 dt. That is what you get. So, you know that integral gt is gt square by 2, and integral V 0, which is a constant, is V 0 t. And you have another constant which is we call x 0. Essentially, it turns out that x 0 is the position at time equal to 0. This is something which you can simply see just as we typically do. So, let us have a look at here how did we do that. So, we had this equation which is dx by dt is equal to gt plus V 0, and we multiply both sides by dt and integrate it. So, integral gt plus V 0 dt, and the first part of this is integral g of t dt plus integral V 0 dt. This is equal to integral g t dt is g t square by 2 plus a constant, and V 0 is integral V 0 t plus some other constant. So, these two constants together, let me call this constant c as a constant c. Now, this c, so basically what you get is x of t. Now, when you put t equal to 0, this term goes to 0, this term also goes to 0. So, c is nothing but x equal to 0. So, c is nothing but x at t equal to 0. So, you substitute this back here. So, you get this particular thing which is x of t is g t square plus v 0 t plus x 0. So, this is essentially what is it saying is that if something is falling under gravity, how does the distance. So, distance, let us say I from this particular point I drop this pen and the distance will increase. The distance from my hand to this pen will increase as the time goes. So, then what you get is essentially x of t, which is this equation basically gives you the position as a function of time. So, you can ask this question by looking at this equation. So, let us have a look at this equation once more. So, basically x of t is g t square plus v 0 t plus x 0. If we know x 0 and if we know v 0 and we know g, which is a constant of is a constant, acceleration due to gravity is a constant. If we know this much, for any time t we can substitute in this equation and get x of t. So, we can get x after 3 seconds is equal to g into 3 square plus v 0 into 3 plus x 0. Now, if we know that x 0 is 0, if we say that x 0 is your height, let us say you are putting from your height, which is, let us say your height is like 1.5 meters. So, let us say you are dropping this pen from 1.5 meters, I can get x after 3 seconds is g, which we know is like close to 10 meter square per second into 3 square plus v 0, and I am dropping it at 0 velocity. At the beginning there is no velocity at all. So, v 0 is 0. So, let us assume in this equation v 0 is 0. So, this is 0 into 3 is 0 plus x 0 is initial position is 1.5 meters. So, if you do this, what I get is 10 into 9, 10 into 3 square is 9. So, it's 90 plus 1.5, 91.5. So, there is a slight absurd thing here, which is this is assuming that the force is there forever, but we have earth after 1.5 meters. So, we have to take these numbers properly, such a way that you put from reasonably good height, and before 3 seconds you would have hit the ground in this particular case, because the answer you get essentially is 91.5 meters. This equation says that if you have such a force, in 3 seconds if there is nothing to stop, it would have gone 91.5 meters. It's a slightly absurd thing, because you are only putting 1.5 meters height and then it can't go beyond that because we have earth. But if you take this from very high, if you drop this pen from a very high point, you can see that it will fall down and the equation will be obeyed. So, do this exercise by taking x 0 as, let us say you are putting it from a top of a building, and let us say how far this would go if you had taken all these constants properly. So, we will do this exercise in the next class, but go home and then also think about what you would get by putting the right numbers in this equation. But as of now, you understood how do we solve this differential equation. So, one important point to remember is, again I am reiterating in the next slide, which is that we have two constants of integration, v 0 and x 0. So, to solve any second order differential equation, any equation of the form d square x by dt square, or d square y by dx square, or d square something by d something square, any second order equation, if you want to solve it, you need to know two constants. To solve a first order equation, you need to know one constant. To solve a second order equation, you need to know two constants. Here it turns out that the two constants in the case of equation of motion, Newton's equations, they are the initial position and the initial velocity, but in some other context it will be something else. but you need to know two constants basically to understand, to solve a second order differential equation. So, basically essentially knowing this, let us summarize what we learned today. So, we learned the first and second order differential equations. The second part of this differential equation is what we discussed today, and we said that how the relation between energy and force can be expressed through a differential equation, and how Newton's equation is essentially a second order differential equation. So, we also learned a bit about concentration, but in the coming lectures we will discuss more about concentration and understand, we will go and understand diffusion, but to understand diffusion we have to discuss how does the concentration vary in the concentration gradient, for which we have to use ideas from vectors. So, we will discuss that and discuss this in one of the future lectures. So, essentially we will go slowly towards diffusion, because diffusion is an interesting phenomenon in biology which we want to understand using mathematics, and for that whatever tools we needed we will develop as we go along, and we will see those differential equations. In the coming classes we will also solve many other types of differential equations and learn a few more different techniques to solve differential equations. So, with this I will stop today's class. Thank you.